Today, we will be discussing the second lab of Physics 2211. This lab deals with the motion of a falling object. The objective of this lab was to observe a real-life example of an object dropped from rest to apply Newton's second law of motion to understand the effective force of gravity and the effective drag force. The motion I observed was a paper napkin ball being dropped from rest and falling to the ground. Then I created a computational model using GlowScript that depicted the motion of the ball with and without drag force. The model used Newton's second law to predict the position of the ball. The computational model and experimental model were compared to understand the effective drag force on an object. My results show that the computational model data that includes a drag force shows a higher correlation to the experimental data than the computational model without drag force, as that graph shows the data points deviating from the experimental data near the end of the time frames. The fundamental principle that is the driver of this lab is Newton's second law. Newton's second law is force equals mass times acceleration. This can be derived further into the equation final velocity is equal to initial velocity plus net force divided by mass times delta t. This equation is used to find the final velocity after a change in time. The computational model uses this equation to update the final velocity as it runs through the program. Derived from this equation is the position equation, which the computational model uses to update the position of the ball as the program runs. This is a recording of the paper napkin ball falling. The ball moves down the screen in the negative y direction. Tracker plots a position versus time graph on the upper right-hand corner of the screen. The plotted points are seen to be curving, and since we know that the slope of the position versus time graph is velocity, the ball is traveling with a changing velocity, meaning f net does not equal 0. Below the graph is a table of position and time points, which are the points I used to plot the experimental data. Using the data that I obtained from the video analysis and tracker, I completed simple calculations that will be used in our code when creating a computational model. The mass is equal to 0.0096 kilograms, which I found by using a scale. The start time is 0 seconds, the final time is 0.633 seconds. The initial position is 0 meters in the x, y, and z direction, as the origin was set to where the ball was dropped from. The final position is 5.33 e negative 2 meters in the x direction and negative 1.697 meters in the y direction. The initial velocity is equal to 0 in the x, y, and z direction as the ball was dropped from rest. The error scale is 21.2585, and this value is used in the computational model to determine how long to draw the arrows to represent vectors. The proportionality constant for the magnitude of the drag force is equal to 0.002545. This was found by trial and error by choosing values and checking if the final position value of the computational data equaled the final position of the experimental data. We take this data and plug it into the startup code given to create the computational model. Here we plug in the ball's mass, ball's initial position, and initial velocity. Then we plug in the value for delta t. It is essential to choose a small delta t because this will yield more accurate results. I chose to use 0.001 seconds as my delta t. This loop will update the position of the model using Newton's second law. Here is the code that represents Newton's second law. Notice that F net is equal to drag force plus the weight force. Weight force is found by multiplying 9.8 by the mass and the unit vector j hat. The drag force is calculated by multiplying negative b by the magnitude of the velocity squared, multiplied by the negative j hat. Every time the code loops through the initial velocity will be updated in order to find the new position at the given time, which represents the shift in the ball's position. Here is where the arrow scale is used to create the arrows that represent the forces acting on the ball. Once the code is run, we get a computational model that is representative of the motion of the ball falling. Taking the data given to us from the computational model, we are able to compare the observed motion and the predicted motion. This graph shows the experimental data that we obtained from the video analysis and tracker, and the computational model data that both includes the dataset with only weight force and the dataset with both drag force and weight force. The gray line represents a computational model with drag force, and the orange line represents the data without the drag force. The computational model data with only weight force deviates from the experimental data near the end of the time frames. This is due to the fact that our object did not only interact with weight force, but also the drag force. The correlation of the computational model with drag data and our experimental data is very strong, as they line up almost exactly. Any deviation can be due to the fact that the drag force constant is not the exact constant that represents the experimental data, as we use trial and error to find a close proximate. Also, this can be due to the fact that the object was blurred when plotting the points in tracker. Therefore, the center of the blur was used, so it is not the most accurate representation of the ball's position. With all of that information in mind, let's consider some conceptual questions. What if we were to have thrown the object down? If the object was thrown down, then the initial velocity would not be equal to 0. I changed the initial velocity in the computational model to imitate the motion of the object being thrown down. I ran the code and plotted the points. Therefore, the graph would have a steeper slope due to the fact that the force of the downward throw, along with the force of gravity, would cause the ball to increase in velocity much faster. The yellow line shows the motion of the object being thrown down. The prediction says that the object should travel farther in the time interval. However, we know that this is not possible, as we have the ground that would stop the object from going farther. So, it simply would fall faster than it would when dropped from rest. After comparing our observed data and predicted data, and considering possible changes and how they would affect our data, we now must ask ourselves, what does this all mean? The slope of the position versus time graph shows the velocity of the object. In our graph, we see that the computational model with drag force line and the experimental data line become linear near the end, showing that the object experienced constant velocity. This velocity is known as terminal velocity, as this is when the force of drag and weight force become equal. The orange line becomes slightly nearer at the very end, but it is not truly linear. This is due to the fact that the line represents only weight force. Therefore, only the computational model with drag force shows terminal velocity.